All right, good morning. Laser Queen, that would be cool. Yeah, Laser Floyd would be classic. Man, I wish I had seen Queen. I had no idea how much I was into them when I was into them. Let's see. Question: should we be using our two-string method in the fraction class, or will you be using it in main? There's probably no place to reasonably use it in your class itself, except maybe for debugging. Um, but there's probably no reason to convert your fraction to a string to do any of the things your class needs to do. But I will definitely be using it in my test main program, probably by just trying to print your fractions. So concatenating strings and passing it to print line. Yeah, you're welcome. Had a question, but need to look at my code to remember what it was. Okay, that's fair. Um, is that the same with two double? Yeah, almost certainly no need to convert your fraction to a double inside your class for any, no need to do that for anything. To do your operations, add sub mul div, you're really just manipulating numerator and denominator and coming up with a new fraction. Um, so yeah, two doubles probably just external. And so if you're still kind of struggling with how this all sort of goes together, um, your multiply method, for example, returns a fraction, and it also takes in a fraction, which you could call something more meaningful than n. Um, and then this thing needs to figure out what your new fraction should look like, which is your current fraction times n, right? So you can make, a new top and a new bottom. And do whatever you have to do to figure out what the numerator and denominator should be of the result of this method. And then you can simply return a new fraction that you construct with those new numerator and denominator. So that's one way the new fraction comes into existence, right? I've seen some people who start off by constructing, just a generic fraction and then change the fractions top and bottom to be, whatever you decide the top and bottom should be. Um, that works just as well too, but keep in mind you have to keep these things in reduced form probably to avoid getting into trouble. So if you do this, you could reduce, the fraction that corresponds to new top over new bottom, and then set the top and bottom of your already constructed fraction. Or you can do it like this and put your reduce inside your constructor. And now, if I've decided this should be 9 and this should be 3, my constructor for a fraction with arguments 9, 3 will set the numerator to 3 and the denominator to 1. But either way will work. With the two double, do we need to something to double to an int? Cast. No, so two double returns a double. So you want to, return the double precision floating point version of numerator over denominator. And the easiest way to do that is something like return but cast one of those to a double and return it like that. But do a check first, right, and make sure that the denominator is not 0. If denominator is 0, this might return nan, it might return infinity, it might return negative infinity. So do this if the denominator is not 0, but check first. If the denominator is 0, then you just return that static field from the double class called double.nan as a special value. Alright, let's see. Remembered question. So like for our multiply method, I guess that not passing it two fractions is throwing me off. Like how it's a dot mult b. Yeah, that's the whole mental shift to objects. And the idea is, you know, if we have a, which is a fraction, then, you know, a dot num is part of that fraction a. That's its numerator. A dot denom is part of that fraction a. That's its denominator. A dot mul is also part of that fraction a. That's its multiply method. And if you think of this as just being, you know, another piece of this object a, what does this do? Well, it takes a number and it multiplies a by it. All right, so we want to get into a mindset of these methods, these pieces of code, as being a piece of the object, just like, you know, these fields are pieces of the object or the structure if it was in C. This code is also part of that object. And you can actually think of it as being, you know, here's my object A. It's got a numerator, it's got a denominator, it's also got a bunch of code. And this piece of code multiplies its argument by A. If I have another fraction B that also has a method called mul, and this function takes the argument and multiplies it by B. So it's a different mindset, it's a different approach to using these functions, and that's what object-oriented methodology is about, basically. Let's see, it seems to return 0 every time I use rational numbers. Make sure that you're casting one of these to a double before you do the division. And if you want to be really sure, you know, you can put extra parentheses and you could cast both of them. Like that. Or do it in pieces, make, you know, double x equal to num, double y equal to denom, and then return x over y, and that'll definitely return a floating point number. But that will also let you look at the values, you know, of x and y and see if it's actually converting or truncating or something. Linux server booted you off. Oop, okay. Yeah, it's an awesomely powerful server. Let's see. Yeah, try casting to double. I need to cast a double on Stack Exchange. Cool. So what do you mean when you write double.nan? So double is a class, right? Double with an uppercase D. And one of the things it has is a number of static fields, and one of those fields is NaN. And so uppercase D double dot NaN is a number. It's a double precision number that is reserved for reporting something is not a number. It's this particular 64-bit pattern, which if you go through the IEEE 754 standard and you try to look at what this is, it's a weird number, right? The mantissa and the exponent and the normalizing, it breaks the pattern. And so this is a reserved pattern for not a number. And so if you say return, you know, double.nan, that's a double value that actually comes back from your two-double function. And it's a value that we're asking you to return to represent that your number was something with a denominator of 0. How do we use the fraction we're multiplying in the method? Inside that method, right? That method is written inside a class, and part of that class is, you know, an integer numerator and an integer denominator. Those are the numerator and denominator of, for example, in this case, A, or in this case, B. So if I'm writing a multiply method, if I just access the numerator and denominator that I've defined in the top of that class, that's the numerator and denominator of whatever object I use to get to this method. And until that sinks in, play around with it. Throw in some print statements inside here. Print out a message. I'm inside multiply. Print out numerator and denominator. And then print out, you know, numerator and denominator of your arguments. And call this from different objects. And you'll see that, you know, whatever object you use to call mul, that object's numerator and denominator are the ones that the code in mul is accessing. So play around with that. Throw in a bunch of print statements and you'll see what's going on. Inside the multiply method, how do we use the first variable? Yeah, so that's what I was just describing. Why did you say we need to cast to a double again? I just declared two different variables to be a double and set them equal. Yeah, so if you set a double equal to an int, that automatically does a cast for you. It sets your double equal to parentheses double name of the integer. So assignment is doing that cast. I think you said we don't include it in the fraction class because it doesn't really fit. No, you do include the two double method in the fraction class. Somebody was asking me if you needed to use two double yourself inside any of your code and stuff, and the answer is no. Two double would get used by something outside, but definitely include a two double method in your fraction class. Double.nan with a capital D and two capital N's, correct. Got my algorithm to find the GCD of 3615, but breaks when I try 1536. That's okay. You can just always make the first number bigger, which is what a lot of algorithms do anyway. But depending on how you write it, sometimes it works automatically, regardless of which number is bigger. But you know, you can write your reduced function and just exercise the heck out of it. Make it public for testing, and just, you know, call reduced with a whole bunch of numbers, and make sure it behaves in all the cases you plan to use it. All right, cool. Really good questions. Anything else? Or anything that I missed in chat? It tries dividing by 0 for some reason, but I did write it on a beach. Yeah, too many starfish. You mean your reduce function tries to divide by 0? I'm guessing. If that's the case, it could be, yeah, so you could write it recursively, which is a little easier than looping. But when you do Euclid's algorithm, so like, you know, 36 equals 2 times 15 plus 6. And then, you know, swap out your variables. 36 equals 6 times 6 plus 0, right? At this point you stop, and this is your GCD. That's not correct. 15 equals 2 times 6 plus 3, and then pull those over. 6 equals 2 times 3 plus 0. Once you find a 0, that's your GCD. If you try to do this one more step, then you'll likely end up with a division by 0 somewhere. When returning a double, do we have to write the data type in parentheses like the cast? Yeah. Unless your variable is a double. So if you have a double and you set it equal to an int, you can just return that variable. But if you have an int and you want to return it as a double, put the double in parentheses to cast it. I'll double check for that. That would have been a good pun, but I know you didn't mean it that way. Maybe you did. Why are they called doubles anyway? What is it that's doubled? More precision. Why double? Why not triple? Yeah, it's the number of bits. So floats are 32 bits or 4 bytes. Doubles are 64 bits or 8 bytes. So double the number of bits, more than double the precision, I think, and much more than double the range. Double scoop of ice cream. Why is a float called a float? That was an interview question I had actually when I was a clerk. Why is a float called a float? What's floating besides ice cream and root beer? Which sounds really good right now. I would so be outside drinking a root beer float if I wasn't teaching. And if I had root beer. The decimal point is floating, right? So there's this old notion of fixed point. And fixed point, you know, you have a number like this, and you just decide, you know, anytime I have a number, the decimal point's going to be right here. And if you have the number 1, that's actually 0.01. And it's a really, really cheap way to do things that are not just whole numbers, but that, you know, look like more like real numbers. So the first calculator I ever had, my family got it like for the whole family as a Christmas present. This was like, you know, early 70s. And it did add, subtract, multiply, divide, and had a little switch you could slide. And if you slid this switch over, a little dot lit up right here after the second digit. And it let you pretend that this was doing more than just integers. And in particular, if you were adding up dollars and cents, you know, it worked great. Didn't work so great for multiplication. But that's a fixed point notation. And it's one way to move from integers to doing something that involves non-integers. But it's somewhat limited. So the more general way is to have floating point, where your decimal point could be there, or there, or there, or way out here, or way over here, right? So that's scientific notation. So that's the float and floating point. If it don't make dollars, it don't make sense. Absolutely. All right, cool, good stuff. Now I can ask you about floating points on exams. No. All right, cool. Let's talk about generics. So we introduced this concept yesterday. Let's see. Do you want us to give a warning that you divided by 0, or silently ignore it? Silently ignore it. That's okay. Last minute's fine. Don't ever print anything from anywhere in your class unless it's really clear that you're supposed to, right? So division by 0, just, you know, set whatever flags you need or do whatever you need to do, but don't print anything. You're welcome. Down for floating points on exams. Yeah, or root beer floats on exams. All right, so let's play with some generics. So let's look at the linked list class. Now we made a linked list yesterday, and we made linked lists of integers, and then we made linked lists of strings. And in the afternoon section, we went a little beyond that, and we made a linked list of rectangles. Except our linked list class was called Potato, because, you know, 2 o'clock in the afternoon. So we made a list, right? We constructed it, and then we added a bunch of rectangles. And then we printed it. And this was exactly like the code that we had yesterday morning, right? Except we were first adding integers, and then we were adding strings. Well, here we're adding rectangles. And how does that work? Well, the code is almost exactly the same. The Sentinel, you know, was constructed with an arbitrary rectangle instead of an arbitrary int or string. The add method said I'm going to take in a rectangle, and that's all that changed in here, right? The way we insert the node in the beginning was exactly the same, and the print method, where we go through from the first node to the last and print them out, that was exactly the same. And I added a little tweak here where we printed the array, but we can just print, temp.data. And then the node is exactly the same, except that the constructor takes an argument of type rectangle, and the node's data field is declared to be a rectangle. So the mechanics of this code was exactly the same as what it was for strings and for integers. Basically, I changed the word int to rectangle. But when we compile that and run it, right, we have a linked list of rectangles. And our print method shows us, our rectangles in a reasonable presentation because it's using the toString method in the rectangle class, which prints out, our rectangles in human readable form. So this is the idea behind generics. One set of code that works almost identically for integers, for strings, for rectangles, and probably, for anything else we could come up with, for triangles and all of that kind of stuff. But with a few differences in implementation. For example, the word RECT here might have to be changed to INT or STRING. And that same word would have to be used here. And there's a few places in this set of code where a particular set of characters that specify the type of something need to change from, say, int to string to rect to triangle and so on. But the rest of the code is the same, so there's a mechanism called generics. And generics let you basically write code that leaves some piece of this code as a variable that you can substitute in when you're constructing and using elements from this class. So I could say, instead of making this a rectangle or making it an int, let's just make it a blah. And have a way to say, okay, now I want blah to be int, now I want blah to be string, now I want blah to be rectangle. Okay, so that's the setup for a generic. And generics work like this. So linked list angle bracket E. This E is the placeholder. When we construct a linked list, we're going to say what kinds of things we want to have in our linked list, and we're going to specify that inside angle brackets. And then all the code that goes into a linked list will use this type in whatever place it needs to use the type of the thing that we're building a list from. And so when you see these specified in the Java doc, it's usually called E. I don't know why. And it's in angle brackets. And when you look at some of these methods, right, where it says, for example, let's add something to the end of the list, the add method takes an argument lowercase e, right? And what type of thing is that? Well, whatever type of thing E is, the type of thing that you used when you constructed the list. All right, so let's do this. All right, I want to make a linked list. My constructor says just linked list. All right, but because it's generic and I need to know it's generic, right, so this would be how I would normally construct if it wasn't generic, and the compiler will tell us. Oh, got to talk about imports. So this business up here in the top of our Java documentation says linked list actually is java.utility.linkedList. So there's this whole namespace of classes available in Java. Lots and lots of classes. Okay, if we come out here, here's all the different packages that are available. Each of these packages contains a bunch of classes, right? So if we look at java.utility, it's got all these different things, right? Including linked lists and some other stuff, but there's linked list in there. And so there's too many classes to make them all available at all times. There would be a huge search space, huge namespace. So there's some classes that are always available, like strings, for example, or uppercase doubles or uppercase integer. But a lot of these classes, we need to say, you know, I want to use the linked list class, which is in java.utility. Now, we could just say java.util.linkedList, but we can also say, you know, if you're looking for a class and you can't find it, search in java.util. And we could say, you know, let's use java.util.star. So I'm just going to do the following. And so the keyword is import. And you just say import and the name of the thing fully specified. So this is the utility package that's part of Java. So if I do that, it can find it. I'm surprised that actually didn't give me a compile error though. Okay. Does Java use namespaces like C++? I don't know enough about C++ namespaces to answer that. But yeah, it's basically like an include, more or less. Although it's not necessarily including this, it's really just sort of like putting it on the radar so that if we encounter a linked list, it will take it from java.utility. Okay, well, I thought this would give a compile error. I was going to use that to motivate what comes next, but it doesn't give an error. So we're just going to go ahead and specify a generic. So let's make a linked list of strings. So I'm going to say linked list string equals new linked list string. And that creates an LL, which is a linked list of strings. And now I can say ll.add. And I can call methods. Right, so I can call the length method, and if we look at a linked list method summary, there's a thing called length. Or maybe size of, or size. So size returns the number of elements in the list. Alright, so we added 3 strings, and it tells us the size is equal to 3. And if we print this out, you know, before and after each add, right, our list is growing. That's not surprising. And we can now use any of these methods on our object LL. We can search for things. We can convert the whole thing to an array. We can insert things at the beginning or the end, and so on and so forth. So I used ll.length to find the length of an array. So if I make an array, there's an array of 17 integers, I can say data dot length. That's a field, okay, in the array. It's not a method. It's not executing code. It's just a number that's stored as part of what it means to be an array called data, and that's equal to 17. On the other hand, if I have a string, right, strings have a method called length. And so I can say, name of string dot length parentheses, and that calls the method. It executes the code that will go through and count up the number of characters in the string or access some field that knows what the length is. So that's a method inside the string class. Right, just this thing right here. So linked lists have a method called size. And size tells you how many things are in the list. How do we know that? Because if we look at the documentation for linked list, there's a method called size. Returns the number of elements. So you got to look at the documentation basically. But for arrays, it's always name of the array dot length. That's standard. But anything else, if you're just calling methods, look at the doc and see what the method is. Cool. Alright, so we can do all of these things to our linked list now. See, as an array, the length is actually stored somewhere. Yes, exactly. In an array, the length is stored somewhere. Probably. I mean, there could be some weird method that's being used where it puts a tag at the end of the array and then it counts. But yeah, it's probably just storing it as a piece of data somewhere in that structure. Again, we don't know how that happens. We don't have to know, right? Is it using magic? Maybe. Long as it works, we don't care. Yeah, magic's always the answer. But in the linked list, it's a method. And you know it's a method because it has parentheses after it, right? And it's in the method section of the documentation. But there's a field called mod count, so I could say ll.mod count, and I actually have no idea what that is, and I suspect this won't tell me. Number of times lists have been structurally modified, so things that change the size of the list. Well, that's kind of interesting. I'm not sure why I would need to know that, but someone might. So yeah, if it's listed under fields, it's just going to be the name of that thing. But if it's under methods, it's going to have parentheses. That's actually code. So if I wanted to look at each element in my list, I could do something like this. And I could say, element I equals, and I could say, let's get the ith element from my linked list. Well, here, I'm not going to start with the sentinel node and follow pointers. I don't even know if there's a sentinel node. I don't even know if there's pointers, right? I have no idea how this is actually implemented, unless I go and I read the documentation or pull down the source code and reverse engineer it, or go to Stack Overflow or something, right? But we don't need to do that for a linked list that we construct, in this way, because we have all these methods, and we have this really cool method called get, which lets me put in an index and it will get that element out of my linked list. So I can treat this like an array, right? I can just say element I equals, and it's just going to be ll.get I. Alright, so that's one way that we can iterate through our list. And so there's the elements of our list. And this add method, if you look at the documentation, says it's adding to the end of the list. So add will append the specified element to the end of the list. There's another method called add first, which adds to the beginning of the list. So when I said add, um, you know, this is fun, new string here, fun stuff, that's the order they came out in. If I had said add first, right, now I've got the FIFO behavior. I'm adding to the beginning, so the last thing that I added comes out first. There's not an add method that keeps it sorted. Not that I know of. There may be, actually. But if there was, I would need to tell it how to sort things, because this is a generic class. I actually don't know if there's... Yeah. I'm pretty sure there is a way to do that. That's a good thing to dig into. Yeah, good question. So how is this implemented under the hood? No idea, right? Except that it tells us, yeah, bubble sort add, that would be good. It tells us that it's a doubly linked list, so presumably it is actually a linked list with pointers and so on. But we can treat it like an array, right? We can just, you know, add something at position I, or get something from position I, or, you know, remove something from position I. So there's a remove that'll take an index. But with the advantage that, you know, since it is implemented as a linked list, if we try to you know, delete something from the middle of the list, we don't have to move all the stuff down to fill in that space, right? Because it's not really an array, but it will act like an array. So this is quintessential objects, right? This is taking all of the machinery that you need to do a linked list, keeping track of pointers and, you know, having reverse pointers to increase your efficiency and all that kind of stuff, and it's hiding it, right? It's putting it in this closed ball called a class that you have just, you know, a little bit of access to through these methods. And so it makes it easy to use this without having to worry about those details, right? This is how our world is set up, right? This is what a car is. When you get in your car to go somewhere, you're not worried about, you know, the internal combustion engine, the pressure, the spark plug gap, all that kind of stuff. That's all hidden from you. And you have a simplified interface, right, with an ignition key and a steering wheel and some pedals and a gear shift. And that's your interface to all this other stuff. And is the car electric? Is it diesel? Is it, you know, gasoline? Is it fuel injected? Doesn't really matter, right? Well, fuel injection matters. Right. So this is the cockpit of the class, right? The stuff that we get to interact with, and all the implementation details, those are hidden from us. But this means that, you know, if we want a linked list, we just, you know, construct a linked list and we start calling these methods. Right, so this will be PA2. And yeah, cars are increasingly fly-by-wire. So you know, like airplanes, when you turn the it's not called a steering wheel, but I'm not a pilot. When you turn the steering wheel on an airplane, that does not move your flaps, right? Not anymore. That's an input to a computer, and the computer decides what to do. When you hit the brakes on a car, chances are that does not, you know, apply pressure to the brake fluid, which moves the brake shoes to create friction, right? The pedal's probably an input to a computer, and the computer decides what to do. Like, you know, oh, you're going really fast, so I'm going to, you know, slowly increase the brake pressure on this side of the car because your wheel's going that way, and so on. It's all fly-by-wire. So that's a little bit like this, but more fun. All right, there's a toString method in every object. All right, there's no toString method described here under the methods for a linked list, but if you search down through the inherited things, right? ToString is part of a abstract collection. And remember, we can force a call to ToString by just concatenating our object to a string. So if I just print out your list is, and then I concatenate LL, this will implicitly call ll.ToString, take the return from that, and then concatenate it to this string. So if we do that, it tells us your list is. And what did it do? It printed out a pair of square brackets with each element of our list printed, separated by commas and spaces. That's what the ToString method happens to do. If we don't like that, we could write our own ToString method. We could make our own version of a linked list class that extended this version, but had our own ToString method. And would print this out, you know, maybe with just spaces in between. So not only do we have, you know, all this power of this sophisticated class with all these methods and so on, but we have the ability to take this and modify it, right? To create our own version of this by extending it and either adding new things or possibly replacing some of these behaviors. My sister just banged at me and said, "Skedaddle, skedoodle, you are now a noodle." Awesome. That's good comments to put in code, actually. Yeah, you could put that in your reduce function. All right, so let's make a linked list of rectangles. All right, so very little change of the code, right? My linked list, when I specify the type of thing LL is, I put a rectangle in angle brackets. And when I construct, I call linked list, I put the rectangle in angle brackets. And that's the only place I need to do it, right? When I'm using LL, I don't need to keep saying angle bracket rect, because LL has been constructed to be a linked list of rectangles. So you really just specify that, you know, when you declare and construct, and then you just use LL as usual. So now I'm just going to make a set of rectangles and add those by, you know, passing them as arguments to the add method. And then I'll do my loop here where I print out the elements myself, and then I'll use the ToString method to print the list. And I'll pull my rectangle class from the archives. And there we go, linked list of rectangles. So there's the elements we printed out ourselves, and then there's the elements printed out by using the value from ToString. Awesome, yeah. You should invent like new terminology and use it on your calculus professors. Like, I'm having trouble converting this to a noodle. I don't think I have our triangle class anymore, unfortunately. Well, maybe I do. Oh, I do. So what was our triangle class? Oh, nice, nice. Constructor. Finding a constructor. There we go. I don't think we had a constructor that took 2 arguments, though. But we can fix that really quickly. Oh. Oh, and we had this weird add method. Almost there. Oh. We don't have a way to construct square triangles. And we still have our funny print statements inside the constructor, but that's okay. So there's our linked list of triangles. And there it is, printed out by using the toString method. So yeah, this works for pretty much any type of object, right? Well, for any type of object, not just any type. Yeah, the triangle will never go away. Yeah, you could use noodle as a variable, definitely. Or smiley face. Yeah. All right, so that's basically how we use generics, right? It's a general notion. We'll talk eventually about how we can make generics, right? So that we can create classes ourselves that have this generic capability, so we can plug things in. And it's really easy to do, right? You basically, it's just a bit of syntax you have to get down. But basically, you put a placeholder, like E, and then instead of saying int or string, you just say E, and it'll get filled in with whatever the caller used when they say defined or constructed your class. So we'll see later on how to make our own generic classes, but for now we're just interested in using them, in particularly linked lists. So tomorrow is open lab, right? No lecture per se, but I'll be around, and you can work on code. We can ask questions, talk about it, and so on. And then Friday we'll talk about PA2, which I'll get posted today or tomorrow. We'll talk about PA2. We'll talk about hash maps, and we'll talk about doing basic input and output using scanners and print writers, so that we can read in from files, write out to files. And that'll give us most of the pieces we need for PA2 at that point. So we'll go from there. All right, cool. We are out of time. I will leave it at that. Have a good afternoon, and I will see you next time. I'm going to skedaddle. You knew I was going to say that. All right, thanks. Bye.